Hi everybody, this is Math 024, Module 3, Part 3 of the videos. We're going to continue with functions in this video. We're going to look at domains, how to graph functions, and we're going to look at some scatter plots. So we have a lot of things that we're going to look at here. We're going to start off with the domains of a function. Remember, a domain is defined as all the first or the x values, the values that you put into the function. So your domain can be defined for a function. We looked at on a graph defining the function in the last video. And now if they give us a function and they ask us to define the domain, or basically when we do that, we're going to write it. We're going to say what values for x we can put in to the problem, because not all numbers work with every function. So the two main things that we want to look for when we're looking to define the domain, we have problems if we have fractions, because remember, you can't have 0 in your denominator of a fraction. So if you have a denominator in your function and a variable in there, you have to find what values will make that denominator 0, and those are values that are not allowed for the domain. And then also, if you have a radical, an even powered radical, like a square root, a fourth root, we can't have a negative number underneath that radical. So we would look at the equation under the radical to find what would, what values for x would make it a negative number. And again, that's where the domain would be undefined. So for our first problem here, we have f of x equals 4 over x minus 2. And again, because we're looking for that domain, we are concerned with the denominator only. Doesn't matter what's in the numerator. And we can't have our denominator equal to 0. So to figure out what values would make it 0, you're going to take whatever equation is under there and set it equal to 0, and then solve the equation. So we had x minus 2 equals 0. So to solve the equation, I'm going to add 2 to both sides, and I'm going to get x equals 2. So the domain for this function, is all real numbers except x cannot equal 2, because if we have a 2 in there, it would give us a 0 in our denominator, so it wouldn't work. So our domain, again, is all real numbers except x can't equal 2. So we're defining the domain. Now, again, with b, we are only concerned with the denominator. I don't care what's in the numerator, because you can have a 0 in the numerator. That's no big deal. But for the denominator, we can't have a 0. So we're going to take the problem that's in the denominator, the 16x plus 5, set it equal to 0, and then it's a linear equation, so we'll solve it by subtracting 5 first. And we get 16x equals negative 5, divide by 16. So x is going to equal negative 5/16. So again, this means our domain is going to be all real numbers except x cannot equal negative 5/16, because if it's negative 5/16, then we would get a 0 in our denominator. So that's where it would be undefined. So on the first slide, we had some fractions. We were looking at the denominator not being 0. Now we're going to look at some radicals. And remember, underneath the radical, we cannot have a negative number. So when we go to set up these to define our domain, we're going to take the problem under the radical, or the equation. So 3x minus 2. And we know that x, when we solve it, has to be greater than or equal to 0. So it can be 0 or anything above. It just can't be a negative number. So it can't be below 0. So we set it up as an inequality, and we're going to solve that. I'm going to start by adding 2. We'll just solve it like a regular linear equation. So we get 3x is greater than or equal to 2. Divide both sides by 3. So here, our domain is x has to be greater than or equal to 2/3. So our x has to be greater than or equal to 2/3, and that would be our domain. So we would describe the domain that way. It's a little bit different than before, where we had just a single number we couldn't include. Here we have a whole range of numbers. We know that x has to be greater than or equal to 2/3. Let's take a look at D. It's the same type of problem. We have that 2, or the square root, which is our even index. So we're going to say that 10 minus 19x must be greater than or equal to 0. So I'll start off by subtracting 10 from both sides. So now I have negative 19x is greater than or equal to negative 10. And then I need to divide by a negative 19. Because I am dividing by a negative number, remember your rules for solving inequalities. When you divide by a negative number, you have to flip that inequality sign. And then here, the two negatives, negative 10 divided by negative 19 will make that positive 10/19. So here, our domain is x has to be less than or equal to 10/19 in order for us to get a positive number under that radical. So any number that is less than or equal to 10/19 will give us a positive number under that radical. Okay, so now for E, we actually have a denominator and a radical here in our function. So now we're going to treat it like a radical. We're going to take our 7x plus 4, and we know it has to be greater than 0, but in this case, because it can't be 0, we're not going to put the line underneath. We're not going to say greater than or equal to. We're just going to say it has to be greater than 0. So I'm going to start off, I'll subtract 4 from both sides. So we have 7x is greater than negative 4. Divide by a positive 7, so I don't have to flip my sign. So here, x has to be greater than negative 4/7, and this would be my domain. Right, now for F. When we're looking at a domain and to define the domain, we're really looking for, are there any fractions with variables in the bottom? And in this case, there are no fractions with variables in the bottom. And are there any even numbered radicals? So square roots, fourth roots, sixth roots, and there are no radicals here. So for this problem, we already know it's a function, and there's no denominator or radical to worry about. So our domain here is going to be all real numbers. So it's all real numbers for our domain. And there's no fraction to worry about or no radical. So we don't have to do any solving. It's just going to be all real numbers. Okay, so here we are going to work on graphing. And the first thing we're going to do is we're going to start by graphing by hand, and then we will look at some where we graph on the graphing calculator. And when I do that, I will post like a separate video to show you the steps that you would use on the graphing calculator to graph. So we're going to graph f of x equals 2x plus 1, and they've made a t-chart here. Remember, our t-chart is this right here where we have our x, and remember f of x is the same as the y value. So they've given us some x values, and we're going to plug them in to find the y values, or f of x. So first we're going to do 2 times negative 2 plus 1. So negative 2 times 2 is negative 4 plus 1, which equals negative 3. So negative 3. 2 times negative 1 plus 1 is going to give us negative 2 plus 1, which is going to give us a negative 1. And then 2 times 0 plus 1 is going to give us, 2 times 0 is 0, plus 1 will give us a 1. And then 2 times 1 plus 1, and again I'm just taking my x values and plugging them in, will be 2 times 1 is 2, plus 1 is going to give me 3. And then 2 times 2 plus 1 will give me 4 plus 1, or 5. Okay, and each of these right here have made an ordered pair. So like the first one, the ordered pair I'm going to graph is negative 2, negative 3. And then I'm going to graph negative 1, negative 1. We are going to graph 0, 1, 1, 3, and 2, 5. All right, let me use a different color here. So again, my stylus is not always perfect, but you'll kind of get the gist of it. So negative 2, negative 3 will be right here, I believe. Negative 1 is right there. 0, 1 is right there. 1, 3 is right there. And then 2, 5 is right there. So now that we have those points, we need to draw our graph. So we're just going to draw a line through them. Again, my stylus just doesn't like a straight line. But that would be our function graphed. So we used the table of values to find f of x or y, and then we plotted those points. Now, typically to plot a graph, you need at least, I would say, 3 points. More is better because you can really see the shape of the graph. Okay, and here we are going to graph x squared minus 3. So, and again, they gave us the x values. We're going to plug those in to find g of x or y, the range. So we're going to start off with negative 2 squared minus 3. So negative 2 squared is 4. 4 minus 3 equals 1. So that goes there. So that should be a 1 right there. And then we have negative 1 squared minus 3. So 1 minus 3 is going to equal a negative 2. We have 0 squared minus 3. 0 squared is 0. Minus 3 will give us negative 3. We have 1 squared minus 3. So 1 minus 3 is going to give us another negative 2. And then 2 squared minus 3 is going to be 4 minus 3, and it's going to equal a 1. So again, we have our ordered pairs. The first one's negative 2, 1. And we have negative 1, negative 2, 0, negative 3, 1, negative 2, and then 2, 1, and we're going to graph those. So we have negative 2, 1 is right there. Negative 1, negative 2 is right here. 0, negative 3 is right there. 1, negative 2 is right there. And then 2, 1 is right there. And because this is x squared, you should recognize that that's going to be a parabola shape. It's a quadrilateral. So we're going to draw our parabola. It's going to look like that. I'm going to sketch it. And that is our function graphed. All right, so our next function that we are going to graph is h of x, and that is equal to the square root of x minus 1. So we are going to do the square root of 1 minus 1, which is going to give me the square root of 0, which equals a 0. Then we're going to do the square root. The next x value we're going to plug in is 2. 2 minus 1 equals the square root of 1. And you always do the work under the radical, then take the square root. So the square root of 1 is 1. Then we're going to do 5 minus 1, and that gives me the square root of 4, which equals 2. And then we have the square root of 10 minus 1, and that's going to equal the square root of 9, which equals 3. So I'm going to plot my ordered pairs. First is 1, 0, so that will be right there. Then we have 2, 1, which is right about there. 5, 2 is there, and then 10, 3 is right there. And a radical, a square root graph typically looks like it's like half of that parabola. It's kind of hard to envision, but there is our function graphed. Okay, and now we are going to look at the absolute value of x plus 3. So remember, absolute value is the distance a number is from 0 on the number line. So the absolute value of negative 2 plus 3 is the same as doing 2, because negative 2 is 2 spaces away from 0. And I always think of absolute value, it's the distance a number is from 0. When we talk about distances, we don't say, oh, it's negative 5 miles away. It's either 5 miles away or it's, nothing. So it's going to be 2 plus 3, which is going to give us a 5. Then we have the absolute value of negative 1 plus 3. So the absolute value of negative 1 is 1. 1 plus 3 will equal 4. Then we have the absolute value of 0 plus 3. 0 is 0 spaces away, so it's 0 plus 3, which is 3. Absolute value of 1 plus 3. The absolute value of 1, it's 1 space away. Plus 3 will give us another 4. And then the absolute value of 2 plus 3. So it's going to be 2 spaces away, so 2 plus 3, and that will give us 5. And then, like we saw before when we were doing the vertical line test, our absolute value is a V shape. So when we plot these, let's see, we should have -2, 5. It's up here. -1, 4, 0, 3, 1, 4, and 2, 5. And then you draw that V shape. And that is what our absolute value graph or function would look like. Okay, so next they ask for us to graph these and sketch the graph. So I'm going to enter them into my graphing calculator and sketch the graph. I will post a video separate from this where you can see how I entered them into my graphing calculator, so you kind of know how I got the answers. So the first one would be -x squared plus x. And when I graph that, and I'm going to use the standard window, okay, our graph, and again, this is kind of a sketch, so you'll kind of see it when you look. It looks similar to, hold on, there we go. All right. Similar to this, and that's not perfect, but that's what the sketch looks like. Next, we have x to the 3rd power plus 1, and when we graph that, it is going to look like this, and it's going to go up through -1, and then through 1, and go up this way. So that's what it looks like when we sketch it. Next, we have 1 divided by x. And when we graph that one, it is going to be, and it's not touching this line, but it's riding right along this line. And like that. So it looks similar to that. Not the best sketch there, but that's what it looks like. And then our last one that we have is the square root of 5 minus x. And when we graph that, it's going to look like this. All right, it should be more curved out there, not flattened out. All right, but that's what it looks like. All right, and again, I will post a video to show you what it looks like on the graphing calculator, like how you would graph those so you can see them. But they just wanted us to give a rough sketch, so that's just a rough sketch of what they look like when we graph them. Next, the last thing we're going to do for this module is look at scatter plots. And a scatter plot is a graph of the ordered pairs in the relation. And we can use these to see patterns and trends in data. So we have here information from the total profit of a small car detailer, and that profit is in thousands. So like the 2 represents $2,000, the 6, $6,000, recorded after a certain number of months. So they want us to create a scatter plot for the data and label the axes. Now think of the month as like our X and the profit, the Y. So the number of months, you're hoping it's a business that each month it goes up in profit. So let's take a look and draw our scatter plot. Now our months are our X values. So that is going to be, again, here's my coordinate plane. And we always got to start at 0, 0. So here's the Y, here's the X. Start at 0, so we have months, and we have to go up to the 11th month. So I think I can count probably by ones. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and we'll put that 14 on there. So that's 1. I'm going to count by 2s here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we'll have 13 on there. Okay, and we have to label the axes. So we have months. Okay, and then the Y value, it goes from 2 to 21 on ours. and that's in thousands. I'm feeling like we should maybe count by twos on here. So every hash mark will be $2,000. I might need to make it a little bit bigger. So like this would be 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14, 16,000, 18,000, and I do need to make it a little bit taller. So let's fix that. Okay, so we have 16,000, 18,000, 20,000, 22, and then we'll put 24 on there. We can. Okay. So let's plot our ordered pairs. The first one is going to be, oh, and this is, when we label it, it's going to be profit for the label of the axis, and then we'll put in the parentheses in thousands. Okay, so we have our ordered pair 1, 2, so 1, 2 would be right there. Then we have 3, 6, so I got to 3 up to 6. 6, 11, so 6, and then 11 is roughly right in there. We're going to kind of estimate it. 7, 14, and again, if you have graph paper, this looks a lot better. Mine is roughly sketched. 11 and 21, so that's going to be all the way, I feel like, up here. All right, so there's our scatter plot. And we can put a title up here, small car detailer profit. We'll call it car detailer profit. I know it's messy. Okay, so we got a label for each axis, and we have title. Now, does it represent a function? And if I look, it would pass the vertical line test. Each x value has only one y value. So yes, it does. They want us to approximate the car detailer in month 14. So if we kind of look, it's kind of going up linearly. So if we keep going, all right, month 14 was right there. So it'll be right around here. That's 24,000. It might be up a little bit higher. It might be about 26,000. I'm going to say 26. And again, it's an estimate because we're looking at a graph. Like I said, if you have graph paper or even on notebook paper, this will look a lot prettier than sketched on here. So I'm going to say about 26,000. And then use the scatter plot to approximate what month the profit will be 18,000. So here is our 18,000. So if we go out, all right, and I look at that, and then I go down, I'm going to say it's about month 8. So approximately the profit will be 18,000 in month 8. All right, so we sketched it. We looked at it to answer some questions. Again, not the neatest thing, I apologize, but hopefully gave you some good idea of what to do with that scatter plot. Okay, now we are going to look at one more scatter plot before we end this video. And this time we are looking at a scatter plot for an athlete's pulse after exercising. So I'm going to draw my X and Y axis. Let me add this. There we go. Okay, now draw it. Okay, and again, we have to always start at that 0, 0. So we're going to label it the athlete's pulse after exercise. So that's going to be our title. Exercise. Okay, again, it will look much better on yours. Okay, this is going to be our X, and this is going to be our Y axis. So X is going to be time elapsed, and then the Y will be in the pulse, and it will be in beats per minute. Okay, so time elapsed, we go up to 3 minutes, so we can definitely count by ones there. So we have 0, 1, 2, 3, 4, 5, 6. So 1, 2, 3. And you always want to go out a little bit beyond what they gave you. Now our pulse goes up as high as 130 and as low as 56. So I'm thinking we have to go up to 130. I'm going to count by, I feel like 20s would be good here. So we have 20, 40, 60, 80, 100, 120, 140, and that's our highest value. I'll put 160 on there. So this is again 20, 40, 60, 80, 100, 120, 140, 160. All right, now let's go ahead and graph our ordered pairs. So our first one will be 0, 1, 30. So it will be right here. All right, then it's 1, 104, so right about there. 2, 82. So right about there. 3, 56 is right about there. All right. Does the scatter plot represent a function? And I would say yes, it does, because for each x value, there's exactly one y value. And then use the scatter plot to approximate the pulse after 2.5 minutes. So this is where I kind of like, I'm going to draw a line here to just kind of see. It's kind of a linear thing. 2.5 minutes would be, right about here. So I'm going to approximate the pulse, and it's going to be right here. So I'm going to say after 2.5 minutes, it's going to be like maybe 75. And again, it's approximation, so there's going to be some leeway in your answers when you're looking at things. But as long as it's in the ballpark and reasonable, then it works. So I'm going to say 75 beats per minute. And then use the scatter plot to approximate the time elapsed when the pulse is 0. So if I continue out this line, I go down, it's like close to 5 minutes when that pulse is 0. But is this logical? So if it continues down like this in this downward spiral, is that logical? I want you to think about this. We're talking about an athlete's pulse. If your pulse is 0, what's wrong? Hopefully you're like, you're dead because you don't have a pulse. You're right. So eventually, because we're dealing with an athlete's pulse, it's going to find a spot where it's going to, level off. It's not going to go any lower. You're going to reach your resting heart rate. So it would never equal 0 unless they were in a lot of trouble. So it's not logical for this graph because of what we're talking about. For other things, it might be, but not for this. All right, that is it for the last and final video for Module 3. Again, I will post the video of the graphing calculator, but this is all of the notes for Module 3. Goodbye.